Good morning, guys. So today we will actually go for the entire review of the mod 7 and 8. So I will also be covering two more topics, which is the conservation of angular momentum and the equilibrium also with the examples, and we can go over it again on Monday. Okay, now to get on with it. So the first thing that we understood in this module was the center of mass concept, where when we are considering an ensemble of particles, to convert that entire ensemble particles into just one entity, we use the concept of center of mass. So you may understand the center of mass as the weighted average of the positions of each and every particle. So the basic definition for for any dimension is this. Okay, for example, if you have positions left here, so let's say this is M1, M2, M3, and then dot dot dot. Let's see, this is Mn. So each one of them is placed at every different position. Okay, so this is x1, x2, x3, xn. Okay, similarly, same thing for the y-axis. We do the same. Okay, this is the same thing. If you go for the height again now, for the height, it'll be like this. So this is y1, y2, y3, and dot 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 yn. Okay. Now, if you want to write both of them in one go, which is the vectorial form, which is the actual thing, we go for the R center of mass, which is nothing but the x center of mass in the x direction plus y center of mass in the y direction. That's it. Okay. Now, leading from here, since we understood how to convert an ensemble of particles, so what we basically did, we converted this entire ensemble and converted into this big blob, which has a new position, which is a center of mass position. Okay. So now we are dealing with only one particle, which we know how to deal with. Now, furthermore, uh, from this concept, we basically went on and understood that if we know the center of mass, then obviously from the center of mass, we also know the center of mass velocity. Now, from the center of mass velocity, it is nothing but very simple, is the velocity of each direction. So let me go step by step. So let me go the position, center of mass, and velocity. So the velocity is gone is Vx center of mass is again same thing, Vx1 plus m2 Vx2 plus dot 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 Vx3 by the total mass m. Total mass m is this. Okay, write it clearly. Okay, the same thing for the y. I'm sorry, I just noticed that it is. Okay, now from here on, we next went on and understood that the most generic or the most general expression for our force. So now let's ponder on the Newton's second law in a new form. Now we know that the Newton's second law as F equal to ma, but the most generic expression for the Newton's second law is a force which changes the momentum per unit time. Okay, so I think we have not yet introduced momentum, but yes, it's a review, so we all know what's momentum. Momentum is the quantity of motion. So this is the most fundamental concept, and everything is related to this kind quantity of motion. Now, the force, the new force, is again is related to the quantity of motion of any object. Now, again, this quantity of motion will actually spit out two expressions in which where mass is constant. So hence, if I just express this and take out the mass, we get the good old expression m equal to m times a, right? And the second one, where the mass is not constant, but the velocity constant. But what is happening with the mass? The mass is a variable, sometimes a ball hitting a wall, so the change of flow is happening there at a constant speed, or a jet fuel which is ejected from a jet at a constant rate. Everything has a constant change of mass or variable mass, and that also constitutes the force. Okay, now from this equation of force, we basically derived a new quantity, what we called an impulse. Now, impulse is nothing but of area under the curve of a force time graph. Okay, so if there is a force time graph, a variable force, so the impulse is nothing but the area under it. Okay, so we understood this like catching a ball. We basically understood that by a force time graph, that how you are changing. So the result is same. The result is when you're catching a ball, the result is the momentum is changing, or there is an initial momentum of the ball which has m times v, and then you're stopping it. So the final momentum is zero. So the net result is same, that there is a velocity and it's stopped. Now the whole point is how it is stopped. Either so you're stopping it by instantly by a stiff hand, you're just stopping it and giving an immense force for a very short time, and then you're stopping it, or you are smearing out the force over a longer time and then you're stopping it. Okay, so this entire game is basically the product between the force and the time given to it. Okay, now whenever, again, please remember, whenever the impulse is asked, you have to resort to this. You just, the first thing that should come into mind whenever the impulse is on is it's asking you the change in momentum, and momentum is again a vector quantity. So whenever you're forming the momentum, it has to be the x and the y, and then you have to go forward with the expressions. Okay, now furthermore, so after impulse, we then went on and pondered on Newton's first law. Now Newton's first law was what? Now Newton's first law is when there is no force acted on an object, the object remains in its inertial state. Okay, that means this basically gives me the change in momentum is zero. Now let's try to ponder on this a bit. So if you're talking about a singular object, a ball, a box, anything, yes, then obviously initially if the velocity is zero, the velocity remains zero, or if the velocity, it has a velocity, then it remains in that velocity, right? But now if I'm talking about an ensemble of particles, so how did we treat that? This momentum for an ensemble of particles is a particle treated as a system. Okay, this changes to the center of mass. Now, invoking our initial velocity expression, which we had like this. So our velocity expression for center of mass was nothing but, so I'm going for the vectorial because you can just add them up, uh, the x and the y. Okay, so in this, what happened? You take the total mass on the other side, and then you get this expression. In other words, the total momentum of a system is nothing but the momentum of the center of mass. So when we are talking about the change in the center of momentum is preserved, or the center of mass momentum is preserved, we are basically mentioning this. Okay. Now this basically encapsulates your entire chapter 7. In other words, let me just make a table. So your chapter 7 basically has three main concepts. One is the center of mass concept, right? So the center of mass concept comprises of this expression, which we just did, right? Same for your y. And then if you're writing as a vector, this becomes center of mass x plus y center of mass y. The second thing that we understood, which presides from the concept of momentum itself, m times v. This basically constitutes two concepts. One is impulse, sorry, one is impulse, which is change in momentum. This basically gives us the impulse, and also it is nothing but the force under the force time graph. Okay. The second thing that we understood is from the Newton's first law is the conservation of momentum. Now, conservation of momentum is nothing but taking the above expression of f going to 0, but now we are treating, we are not only applying the conservation of momentum on our individual particle, but we are also doing it for an ensemble of particles. So this basically conservation of momentum comprises of the delta P is 0. This is for an individual system or object, if there's only one object in the system, or if the entire system comprises of many small objects, then this goes to the change of center of momentum, center of mass, sorry, center of mass. So this is basically what is your entire module 7. Okay. So we did, in total, we did at least 2 to 3 problems. So let me see if I can find those problems and at least describe the most pressing one. Let me see. Okay, let me catch hold of at least three things. So we can have this and we can discuss this. Okay. 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 Again, so the first example is basically the example for the impulse. Now for this, we know that impulse is a change of momentum. So our first thing is to calculate the momentums itself. So in order to do that, what we do, we first draw out the momentums very clearly so that we understand that in terms of the vectors that we know. So this is where your knowledge of the vector is very important. So the moment you understand and write down your momentum very clearly in the vector form, and you do the vector algebra, which is vector subtraction here in this problem, then you're pretty done. So in this, what we are doing, so we know the initial momentum is given as the magnitude and the direction. The magnitude, we know it is a mass with the velocity 1, which is already given to you, which is vi. Let's say vi. Okay. And the direction is, it's in first quadrant. Now the first quadrant comprises of theta 1 x hat plus sine theta 2 y hat. Sorry, sine theta 1 y hat. Okay. This basically gives us pi cos theta 1 and pi sine theta I sine theta 1 y hat. Okay. Similarly, I'll just write down the final momentum, which is this, where we had pf and mvf, and the pf is given as, it's in the fourth quadrant. So fourth quadrant is written as cos theta 2 minus sine theta 2. Okay. The pf is again given as the product of these two, cos theta 2 x hat minus pf sine theta 2 y hat. Since we basically wrote these two, now we understand. Now we will do the subtraction. Now the subtraction comes out to be the final minus initial. Okay. This basically came out to be, although I'm writing the results, guys, I would please urge you to do the calculation very clearly and come to this same answer. Okay. You will see the y-axis will eventually add up. Okay. Now, once we understood what is the impulse, the second part is basically to understand the force. Uh, so the time is given to you, the time of contact, which is this. So in order to do that, you have to calculate the magnitude. Okay, it's actually asking you the magnitude of the average force. In other words, it is asking you to calculate the magnitude of J. So what is the magnitude of J? We know this is the x component of J. We know this is the y component of J. Okay, in other words, the x component looks like this, and the y component is this. Okay, and then what you do, you just take the magnitude. Please remember, every vector is a hypotenuse, and the magnitude is the value of the hypotenuse of the x and the y. Okay, so this is all about the impulse and the force. And then we have the momentum here. Now for the momentum here, you will be, most of the time, it will be one dimensional, then you don't have to worry about the directionality, but you just have to worry about what kind of one momentum conservation of momentum you're doing. Is it one body going to two, or two body going to one, etc., etc. Okay, so for this is kind of taking it, or to the next level. So in this, whenever you're dealing with this, so if you're given an image like this, if you're given an image like this, first of all, identify what you don't know about it. So in this question, we basically knew what is a momentum. So again, as a logistical uh, thing, I would recommend, instead of whenever you're dealing with momentum, instead of dealing with M and V individually, you deal with P. So for example, in this, when I say that this velocity and the mass is given, that means we actually know what is PFC. So I'll go with handling this PFC itself. But in the other one, let's say for the B, you do know the mass, but you don't know the velocity. So in other words, you don't know the momentum. So I will basically say that, oh, I don't know the momentum. You don't have to necessarily go and say, oh, you know what? I know the mass, but specifically I don't know the velocity. So if you don't know velocity, you don't know the momentum. So it's as simple as that. Okay, so either one. So even if you knew the velocity and you don't know the mass, again, it's the same thing. You don't know the momentum. So it's better to go for one thing. So in this question, in totality, we don't know the velocity of B and A. In other words, we don't know PFA, and we don't know what is PFB. Understood? Now, when you do that, so basically you don't know this, you don't know this. But you don't know this and you don't know this, right? But this is perfect. And you also don't know what is X and Y. So since you know the angle between each vectors very precisely, you make one of them as your direction. Okay. In this case, it was the the A direction. So this is the coordinate decided. You could have easily gone for this also. There's no harm. Okay. But when you do that, then you have to calculate all these vectors with respect to this. So for example, if we did this, let's say, so this is 130 minus 90. So this basically became the theta C. This became what? This became 40 degrees. Okay. And this, the theta A, became what? So this is basically 100 degrees from this, right? From theta C. So if this is 100, and so you may have, so let's go for this. So this is 100, this is 40, obviously this is 90. So this basically becomes your 50 degrees, and hence this is 50 degrees. Okay. So obviously so your geometry comes into the play. So it's, you just have to spend a bit of time when you're doing that. But yes, when you will be given a question like this, most probably the angles or the coordinate space will be given out. But I'm just saying, if it is not, then you have to be very good at your geometry. Okay. But the trick is, I'll give you the trick. The trick is, you choose one of the unknowns to be your axis. Okay. Just choose one of the unknowns to be your axis. Okay. So most probably in your two dimension, there will be two unknown. Okay. For 2D problem, this thing you need to understand. For 2D problem, there will be two unknowns. And the second trick is, one of the unknown should be your axis. Understood? So this is the two things that you need to understand here. There's two basic things that you need to understand here. Now, since we understood this and we got to know what are the relative angles, now The only thing is we know that it's a conservation of momentum because there's the the situation is that there's one coconut which got broken out and then gone to three parts. Okay, hence the three momentums are given as, so the PFA is PFA and the direction of PFA, which is very simple, is in the minus x direction. PFB, again, it is in what? PFB is in the fourth quadrant. So PFB is cosine theta b x hat minus PFB sine theta b y hat. PFC, again, this is PFC times the direction, and this is in the first quadrant. So PFC cos theta c x hat plus PFC sine theta c y hat. And since we are talking about the conservation of momentum, so initially your center of mass is 0, which will result in the final center of mass is also 0, which results in PFA plus PFB plus PFC, right? So when we add them up, this comes out to be PFC okay, and then you had the sine theta. Good. Now, when we are talking about 0, this actually says for a more than one dimension, this actually says that each component is 0. Hence, we have to equate each one of them to 0. And you now, it will be very clear for you why we did the direction trick, because here you see easily your B is isolated. Once your B is known, then in the equation you know this, then your A is isolated. Okay, so I'll just write down the result from here. I think that is also there in the previous slides also. So just for completeness, let me write it down very fast. Okay, and here this is also PFC, which is cos theta C plus cos theta B, not cos theta B, this will be sin theta sin theta C over tan theta B PFA. Okay, good. So this basically encapsulates our entire chapter 7. Now let's go for the chapter 8, which is the circular motion or rotational kinematics. Now for rotational kinematics, the entire kinematics hinges on a simple geometric relationship, which is this. So you have an arc, radius. So entire thing hinges on this relation. Okay. So main thing you also have to remember that the arc and the radius. So for a particular circle, for any particular circle, the arc increases for any difference in theta. For any difference of theta, you will see the ratio of the arc and the radius remains the same. So in other words, if you go farther away, your arc also increases. If you go closer, your arc decreases. Okay. So these are the kind of connections that you have to realize when you're doing with rotational kinematics. Okay. So from here on, we also derive that the angular velocity also there. And then you have the alpha, which is the rotational, sorry. I'm doing errors. The tangential velocity, and then you have the tangential acceleration. Okay. Furthermore, we basically, starting from a linear thing, we also understood that all of our linear equations basically will end up giving us the same equations for the rotational kinematics. Okay, okay. Let me go for this is omega f square, and the final is the delta theta is half of omega f plus omega I, or t. I think we were going for t. Yeah. Okay. Two more things. Since this is a vector, although it is a one-dimensional vector, the convention is counterclockwise. Counterclockwise is positive. Your clockwise is negative. Okay. And the final one is that your linear accelerations will have now two parts. So the actual acceleration, if I'm talking about, it will be a result of the centripetal acceleration and the tangential acceleration. Okay, so in other words, in any rotational dynamics, let me go for this thing. Any rotational dynamics, you have two accelerations. One is the central one, and then you have the tangential one. Sorry, this basically results in the resultant acceleration. Okay, and what is AT? You already know what is AT. So your centripetal acceleration is given in terms of the angular velocity is this. Okay, understood? So just keep in mind, if your object is rotating or is under the influence of an angular uh, acceleration, that means if it is in the influence of a angular acceleration like this omega will be the instantaneous omega. So your centripetal acceleration will increase, but your tangential acceleration will be a constant thing because this is constant. However, this will change, okay, at every time. So just keep that notion in check. Okay, good. Now, moving forward from the rotational kinematics, we enter into the concept of rotational dynamics. Okay, now for rotational dynamics, let's try to understand what this is. So, from rotational kinematics, we first the first thing to understand for the rotational dynamics is to understand the concept of inertia. So the concept of inertia in the rotational dynamics is known as the moment of inertia, or in other words, how the mass is distributed over the axis of rotation. Okay, okay. So the moment of inertia is for a discrete object is defined like this. So let's say you have the axis of rotation. Okay, let me just give me a sec. Okay, so if the object is at a distance r, so the moment of inertia around the axis of rotation, and this is the axis of rotation, axis of rotation, then the moment of inertia is given like this. Now, this is all about a discrete object. If you have a system of discrete objects, you just add them up. If you had different objects like this, and then you had this, right? So the total moment of inertia of the system comes out to be is the individual, or you add up the individual momentum inertias. Okay. Now this is basically when you understand that fine, you have two or three more discrete objects and you basically add up the moment of inertia. But now if you're dealing with a composite object, okay, now if you're dealing with a composite object, you will be given the moment of inertia. Okay, but please remember, when the moment of inertia is given, you have to pay close attention that around which axis it is given to you. Okay, so most of the symmetrical objects like a pulley, which is a disc, a pulley is nothing but a disc. Okay, so I don't know why this comes out to you, but tilted, which is quite irritating. So just give me a sec. Let me just draw up. So a disk is nothing but something like this. It's kind of a disk like this. I'm trying to draw as accurately as I can. So it's a disk, and the axis of rotation goes through it. So it's around the center of the disk. So the moment of inertia for a disk through its center, which we will be using again and again, is this, where this is the radius of the disk. Okay. Now, this thing goes for any kind of, so most of the static kinematics, or we will be doing two more problems in this, most of them will engulf your moment of inertia expressions like this. Okay, so for a sphere, it basically comes out to be it again. It is going through the center. It is 2 by 5 mr square. So let me just draw that. So if you have a sphere, okay, a sphere, and the axis of rotation goes through the center. So your moment of inertia is given like this. This is for a sphere. Okay, so everything will be around the center of mass until unless it is specified, specifically for a rod, which I've already told. Now, since we understand what is moment of inertia, let's try to understand the interaction, which is the torque. So, in other sense, we understood what is mass. Now, let's try to understand the relationship of mass and angular acceleration due to a force. Okay, so the next concept is torque. Okay, now torque is, let me just give you the expression, the its radius times force sine theta. Now let's try to understand this. So you have an axis of rotation like this. Okay. Let me just do it on the top down notion. So if your axis of rotation is something like this, which is going through the screen and coming towards you, and the object is here. Okay. So let me just take a composite object. So object is like this. Okay. Now if the force is applied on this point, which I can just extend it like this. Okay, so the R that you see here, you will not take the entire length. This you will not take that. The R that is going should be taken is from this point of contact till the point of rotation. This is the R, and the vector, that how you draw the vector from the axis to the point of contact. Okay, so the angle between them, these two arrows, this is theta. Is this point understood? Okay, this is theta. Now we basically understood that there are two kinds of interpretation. Let me just go and pick that out. It is easier for me to just select some of them. Okay, so this is where we are. So we understood what the torque is. So the torque has three main points, which is the first is the force which has been acted upon it. Second, where it is acted upon, which is basically the R. And then third, at what angle, which is the theta. Okay, these are the three things which determines what torque is. So let's try to understand in this very simple way. So torque, what we understood till now, it is basically the effect, in the sense that whenever a force is applied on a rigid object, it will end up in giving some kind of torque. To understand what kind of torque it is, we have to understand where the force has been applied, at what position it has been applied, and at which angle it has been applied. Once we are established that, we understand the net torque applied on that object. Okay, there are two ways of determining it. One, either to go for to understand the perpendicular component of the force applied with the point of contact. The point of contact, so in the other sense, you uh, make the point of contact as uh, sacrosanct. So you don't change this vector. You say, okay, this is the point of contact. With respect to this vector, with respect to this vector, what is the perpendicular component of the force which is applied to it? Which is this. This is the F tangential, you may say. Okay? The other sense, you say that no, my force is sacrosanct. You keep that vector. With respect to that, you find out what is the perpendicular component of the radius on which this force is being applied. So you know at which contact where the force is being applied. So you take the perpendicular component of that radius, and then this is the R perpendicular. Okay. Okay. So this is all about how we understand what is torque. Now, since we understand what is the source, let's try to go for the entire effect. So torque, again, torque, we understood the effect, which is happening as R F sine theta. This is the effect. The consequences or the result is an object rotates around the axis of rotation with this angular acceleration. Understood? So first you find out the effect. First you find out the cause, sorry. So first you find out the cause. Okay? First you find out what is the cause of the force, which is this. And then this is the effect. Okay? Let's try to understand this again with an example. I'll do that with two or three examples. The first of which was the falling object. Okay, so we take a pulley with a mass m and a radius something, and then there is a bucket of mass something. It's attached to a cord and falls. So the whole thing is again to find out the tension and the acceleration. To understand the system, we draw out the system again. Okay, fine. So this is the pulley which has a radius r. Okay, now this is small m, this is capital M, or let's say MP. Now let's draw out the forces. We know the mass is under weight, there is a tension in the wire, and then this pulley rotates at an angular acceleration, right? Now, the main connecting part here is we also know that the acceleration of the system is nothing but the tangential acceleration of the pulley. And we know how the tangential acceleration is related. It is this. So we will be using this connecting factor. Okay. Let's try to understand the free body diagram for the things that we already know. So let's go for the bucket. For the bucket, we know there's a tension, there is the weight, and then there's the acceleration. Okay. So from here, we can easily write down this is the expression. We can write down what is W, which is mg minus T ma, right? Perfect. Now let's go for the pulley. For the pulley, first of all, what we have to figure out is the effect. So what is the effect? There is a point of contact. The point of contact is always at the edge of a pulley, and most of the time you will see that this tension is tangential in nature. Hence, the torque applied on the pulley is force times the radius. Okay, this is the, so let's try to understand the R. This is the axis of rotation. This is the point of contact, and the force is perpendicular to it. Hence, this is the torque. Now, what happens due to this torque? Now, we understood the effect, we understood the cause. The effect is this rotates the pulley. Okay. Now, since the moment of inertia of a disk is provided to you, you punch that in. Okay. And you also know what is alpha in terms of the tangential acceleration, which is A over R. Okay, so you know this is for the moment of inertia. So you do the calculation, you find out in terms of this tangential acceleration, you find out the force, right? So you put it back, you have the same thing here. Again, MA plus half MPA. This basically gave divided by M plus half MP A. Good. So the main thing is to establish this and this. So you already know how to establish this. This is trivial in the sense that you first understand this. So try to understand the the cause of the torque for any pulley. So this kind of thing, I'm saying that this can be anything. Like right now, we are taking a pulley, which is a disc. It could have been a drum, which is something like this, and the rope goes like this. Again, for this kind of situation, is the same thing. Or if it is a sphere, sorry, my spheres are very bad. If it is a sphere, and then you have a rope around it, again, you know for a solid sphere, this for each one of them, the torque is T times R. If this is the radius R, if this is also radius R, the torque will be, the effect will be same because all of them, it will be tangential. So just keep that in mind. The only difference comes when you are connecting the moment of inertia. So in other sense, so when you have this kind of symmetrical object, you have the torque times moment of inertia times alpha. What actually comes out to be this moment of inertia is different for cylinder, it'll be different for disk, which is this, it is different for this and this. So whatever changes is this. Okay, so ultimately, for example, for a sphere, let me just take for a sphere, it is 2 by 5, let's say 2 by 5 mr squared. This is the only thing which is going to change. Okay, for these kind of problems. And alpha, again, it will be equal to this tangential. So your tension will ultimately look the same way. Okay, look the same way. It depends, this factor that you see here, it depends specifically what kind of an object it is. This half comes due to it's a disk, this comes due to a sphere, and it will be different for a entire log. Okay, good. Now, so okay, we did this. Now let's go for the Atwood machine, which we did in the last uh, part when we did Newton's laws. Remember, in the Atwood, the nuance was that the disk is massless. Now we are going to take the disk to be massive. Now try to understand here. Previously, this fellow was under the effect of only one tension, which is this. Now it is in the effect of two tensions. Okay, so if we draw out the forces which we did, now here again, don't assume the tensions are same, because now the mass is not, the pulley is not massless. We take the two tensions to be different. Okay, now when we do that, we again draw the forces, which is W2, this is W1. We do the free body diagram for the ones that we already know, T2, and this is W2, and the acceleration is moving up. Again, here we are assuming the acceleration. Okay, so one thing you need to remember here, the direction, now we have to be very careful, because previously, if you notice, I did not talk anything about the direction, because I know that the direction of the alpha is the same as the direction of the torque. Okay, but here, because there's only one torque is applied, that's why I didn't care about the acceleration itself. Okay, here there is more than one torque that we will see. That's why we need to be very careful about the direction. Okay, so in this Atwood machine, the first thing is, we assume that my mass 1 is greater than mass 2. Okay, that's why the acceleration is like this. And then we draw out each of the object, the free body diagram. Okay, now for the free body diagram, we understood for this is T2 minus W2, it's M2A. This is W1 minus T1, M1A. Okay, so these two we already know how to write. Okay, now the ones that we don't know is the pulley. So let's try to understand that. So for the pulley, we will have two kinds of tension. Okay, so let's try to understand for the first one. The first one, the tension is trying to rotate in which direction? It's trying to rotate in the clockwise direction, right? And my acceleration is also in the clockwise direction, right? So it is in the clockwise direction. So my torque comes out to be, the torque 1 comes out to be negative T1R because it's in clockwise direction, okay? However, my T2 again is tangential. The torque due to 2 is trying to rotate it, it's trying to pull it on the counterclockwise direction. Hence, the torque due to 2 will be positive T2R. Okay? Now, as a result, my object is rotating in the clockwise direction. Hence, if I put everything together, I will have tau 1 plus tau 2 is minus, because it's clockwise, I pulley times alpha. So I put everything together, minus T1R plus T2R minus IP alpha. And if I do the negative or the minus sign, because I don't like the minus sign here, so what I do, I'll multiply minus 1 on both sides, which basically will give me T1 minus T2 IPR. Okay. Now again, we do the same thing. We put back what is IP, which is a half MPR squared. We took the alpha. Again, we know what is alpha. Alpha is A upon R, which actually comes from A because your acceleration is again tangential, which is alpha times R. Okay. This basically gives us half MPA. Good? Okay. Okay. So we consolidate all the equations. Okay. And then we do the same trick. We add them up. What we get is W1 minus W2, which is M1 plus M2 plus half MP. We put back what is W1. So it is M1 minus M2 G divided by M1 plus M2 plus half MP. Okay, understood. Now here, just pay close attention what is happening here. Now, if I would have said that the mass of the pulley is 0, okay, this basically ends up in telling us that the tensions are equal. That's why, if you remember, we have to come with a nuance that if the mass of the pulley is massless, then the tension is same, because some tension is actually spent in rotating the pulley itself. Okay, understood? So I'll be doing another example on Monday. and then we will try to understand that. So let's get on to the next concept. Since we understood what is torque, what is how the effect of torque, and we understood two kinds of example, how to go for it. Okay, so the second thing is, since we understood momentum from force, same, you will have angular momentum. Angular momentum is the same like the linear momentum that you had, but if you don't have any torque or any force applied on an object, you have the angular momentum to be conserved. So let's try to understand from the linear perspective. Angular momentum. Okay, so the angular momentum is given as, so let's try to understand. So from here, you have the angular momentum definition is the radius cross momentum, which is radius p sine theta. So if you have an axis of rotation and you have an object which is going at a speed at a certain direction, okay, so the radius is this, okay, and this is the angle. So the momentum is rp sine theta. Now if I maximize this, I know the theta is 90 degrees, so this is rp, and I know this is the tangential momentum, because if we are doing for the 90 degrees, this is 90 degrees with respect to the radius. So this is the tangential velocity, because we know mpvt, and we go for the expression of vt, what is omega. So this is r omega, and hence mr square omega. This actually gives us the angular momentum in terms of the moment of inertia and angular velocity, and which is this. Now again, going for the Newton's first law, where if you don't have a force applied on that object, there is no force, there is no force, there is no torque, there is no torque, there is no change in angular momentum. Okay, which basically is this. So any system where there is no net torque applied on the system, the net torque on the net change if angular momentum remains the same, hence the uh, I, the moment of inertia I, omega I, and moment of inertia F, omega F. Okay, so this is basically I'll be doing one more example on Monday as to elaborate this thing. The only last concept is basically the equilibrium situation. And what is equilibrium? Equilibrium is when your net torque and your net force on a system is zero. That's what we call an equilibrium. Okay, so I'll be doing very specific problems, two problems on equilibrium and one problem on angular momentum on Monday, along with one problem of your torque also, as to elaborate, as to touch base on another kind of system, what we did right now. I would urge you guys to go through and study these two objects, and let me give you a starter of what problem I'll be discussing. And I would like each one of you to come prepared with that. So one is, you have an object kept on a table. I think we did this uh, in our other class when we did the Newton's laws. Okay, again, in this, the pulley is not massless. It has a mass mp, it has a mass mp, and it has a mass or radius. Okay, that will give us two kinds of tension. Okay, a horizontal and a vertical one. So think about how you can go for this one. Okay, and uh, let me also give you a secondary problem. So you have two pulleys, one at the ground and one on the top. Okay, and then there's a box here. Okay, again here the tensions will be different. So this is the M box, this is MP, and this, let's say this is another pulley, MP. Okay, so in all of them, find out the tension and the acceleration. Please try to attempt this, try to draw the free body diagram, try to use the concept that I just did in the two problems. There's nothing beyond them, but I will be discussing them in detail in the class. So there will be, in total, I'll be discussing around five problems. So just be prepared with these two so that I can touch upon the equilibrium problems more. Okay. All right, guys.